For this example, we're asked to look at the dynamics of a garage door that's going to be closed. The garage door is designed such that the top edge A is moving along a horizontal line, smooth. The midpoint of the door is supported by a vertical slot, which is also smooth. It's a spring that supports the middle of the door there at B. It says here that the spring is unstretched when that angle theta is 30 degrees. What we want to do is figure out what the speed of end A is once the garage door, if released from rest at 30 degrees, what the velocity of A is once the door reaches a vertical configuration. So we're going to be looking at change in speed for change in position. That's a natural for the work energy equation. We need the free body diagram because we need to find out which forces, if any, do non-conservative work. So, as always, our FBD is a critical first step. If we look at the forces that are acting on A, we have the normal force of the guide acting on A. We have a normal force of the guide acting on B. We have a spring force, which is going to be acting at point B. And we, of course, have the weight of mg. Considering all the forces which act, we know that NA is perpendicular to the point there at A at which it acts. It does no work. Same way there for NB. NB is going to be perpendicular to the line of travel there for point B, so it does no work. Spring force, weight force, they both do work, but we're going to put those in V. When we get to the point of writing down the work term in the work energy equation, as of right now, that work is going to be equal to a 0. There are no non-conservative forces that do work. So then let's write down the other terms. The initial kinetic energy T1, that's a 0 because it's released from rest initially at rest. T2. T2 is going to be, I will reference this back to the center of mass, so this is 1/2 mv_b squared plus 1/2 mass moment of inertia about b times the omega squared. V1. V1 is the potential due to both gravity and the spring. I will choose my datum line to be the slot through which end A moves. So the initial state, the gravitational potential is going to be equal to mg L/2 times sine of theta. That's how far down L/2 sine theta is the distance below the datum line that B is. So since it's below, it gets a negative sign. The spring is not stretched at that state. The potential for position 2 is going to be mg L/2 because at that position theta is 90 degrees. Again, it's below the datum line that I chose, so I put a negative sign. The spring will add on a positive term of delta, where delta is the amount of stretch in the spring at position 2. So therefore, what we have for the work energy equation of T1 plus V1 plus the work done in going from 1 to 2 by non-conservative forces is equal to T2 plus V2. We lose that. We lose the initial kinetic. So that is, therefore, V1 is minus mgl sine theta. And that's equal to 1/2 mvb squared plus 1/2 ib omega squared. And then V2 is going to be minus mgl/2 plus 1/2 k delta squared. So that is our work energy equation. And we have in terms of motion variables, we have two unknowns of omega and VB. We also need to calculate the stretch in the spring there in position 2. All that's going to come from kinematics. So the relationship between VB and omega that we need is only needed for the final state. So if I draw the door in the vertical position, point B is the midpoint, and we know that B is constrained to be moving in that slot. We know that point A here at the end is constrained to be moving along this slot. If we were to ask ourselves, where is the instant center for that door, we would draw perpendicular to the velocity of A, and that would be along this line here. We draw perpendicular to the velocity of B at B, and we draw the conclusion then that the instant center, let's call that C, is actually at point B. So since B is the instant center for the door, it implies that the speed of B at that position must be equal to 0. And since that's true, since B is the instant center, then the speed of A then is equal to L over 2 times the omega of the door. That's the speed we're asked to find. So if we go back to our work energy equation, VB is 0. For omega, we're going to put in 2 VA over L squared. And finally, we need to say what the stretch is in the spring. So also we'll have that delta. It says that the spring starts out with or has an unstretched length of L over 2 times sine of 30 degrees. It says that the spring is unstretched when the angle is 30 degrees. So I guess L is a bad choice here. This is the L of the spring. So L naught for the spring. The length of the spring at position 2 is going to be equal to half of the length of the door. So in the end, what we have is that delta then is equal to L over 2 minus L over 2 sine of theta. That is the stretch in the spring. That goes in our work energy equation right here. So at this point, we have one equation and one unknown. So what we need to do is solve for VA from the work energy equation. And that's it. The work energy equation we use because we want to find the relationship between change in speed and change in position. It was a matter just simply of writing down kinetic and potential. There's no external work done by non-conservative forces. And the kinematics at the end, the key observation there was that the center of the door at that position is the instant center, and that helps us get the right number of equations for the right number of unknowns.